Okay, this video is about definite integrals with linear motion. We're going to do other problems in the next video. Definite integrals can be used to find the change in a function over time. Since the derivative of displacement is velocity, and the derivative of velocity is acceleration, it seems logical that the antiderivative of acceleration will be velocity, and the antiderivative of velocity will be displacement. Using this logic, and knowing what we know about integrals, we can state this from the fundamental theorem of calculus. And it's going to give us the change in displacement from T1 to T2. Remember, displacement is the distance from where it starts, it being a particle, to where it ends up. And it's important to recognize that total displacement doesn't necessarily equal total distance. The best example to remember this is in a track. If you want to run around an oval track, you start and end at the same point. So your displacement, this way, your displacement is equal to 0. But in reality, you've run the whole 400 meters around the track. So then your distance would be 400 meters. Consider a particle that travels according to this formula here. V at t equals 3t minus 6. For the first 2 seconds, the particle is traveling with a negative velocity. This means that at the 2-second mark, the particle is going to stop and change direction. At some point, the displacement of the particle will actually be 0 when it reaches its original starting point. Therefore, if we want to calculate the distance a particle has traveled, we can't just look at the integral of the velocity function. What we need to use is the absolute value of the velocity function. If v is the velocity function for a particle moving along a line, the total distance traveled from t1 to t2 is given by this integral here. And this means breaking the function into intervals where v at t is less than or greater than 0. So if we're going to do this by hand, the first thing that we would do would be to find the zeros. So we'd set v at t equal to 0. We've got a nice linear function. So t is going to equal 2. Then we're going to find our endpoint velocities. And let's look at t equals 0 and t equals 5 for this example. I just made those up. In a homework question or an exam question, you would have them given to you. So v at 0 would be minus 6, and v at 5 would be 9. So next thing I'm going to do is set up my integral from t1 to t2 of the absolute value of my velocity function. Okay. Now I know I'm going to have 2 sections. So I've got 0 to 2. Here. And then I've got my second section from 2 to 5. V at t dt. Okay. So now really what I want here is I want the positive version of a1 plus a2. So I'm going to draw a little sketch. Let's draw it right in here. So this particle is moving sort of like this here. Okay. I've got right here, this is my first point, this is my 0 minus 6. I've got my x-intercept, 2, 0, and then I know up here is my endpoint. This would be 5 and 9. So I've got my first area in red here, A1, and then I've got my second area here in green, which would be A2. So I've got two triangles there. And I know that the area of a triangle is base times height. So my area of my first triangle is going to be base times height divided by 2. And then I'm going to use the green. So A2 would be base times height divided by 2. And that's going to give me 6 plus 13.5 and 19.5. Okay, this is a simple one because you can look at the intervals that are created. You can also punch this into your calculator. So using math and then 9, that's going to give you the definite integral option. And then if you have an old calculator, you would put in your function. It's important here that you would put in your absolute values, your x, your variable that you're integrating with respect to, and then your endpoints. So 0 to 5. The absolute value symbols can be found in the catalog. So to get to catalog, I'll add that on here. You're going to do second and then 0. And absolute value actually shows up at the beginning. Okay, so let's try another example. The displacement function for a particle moving along a horizontal line is given by s at t equals 10 plus 3t minus t squared, where t is between 0 and 4. First thing that we want to do is find the velocity of the particle at time t. So we know that our velocity is our derivative of displacement, which would give us 3 minus 2t. Check. Next thing that we want to do is find when the particle is moving right, the positive direction, and moving left in the negative direction. So we can do this the same way that we did the first derivative test for increasing and decreasing functions. We're going to set our velocity function equal to 0. Okay, and that gives us our time where the particle is potentially changing from negative to positive. So I've got t equals 3 over 2. Now I'm going to test a value that's to the right, so that's greater than 3 over 2. So let's say test t equals 2. And then I'm going to test a value that's to the left, t equals 1. So let's see, v at 1 would be 1, which is greater than 0. And v at 2 is equal to minus 1, which is less than 0. Great. You could have chosen any value greater than 1.5 or any value less than 1.5. 1 and 2 are easy to substitute in and work with. So when v at t is greater than 0, it's moving right. Okay. And that is when t is between 0 and 3 over 2. And v at t is less than 0 or moving left when t is between 3 over 2 and 4. Okay, the next thing that we're going to do for this one is to draw a motion diagram for the particle. And what a motion diagram means is that you use an x-axis for the time and you draw on where the particle moves. So what we need to do is we need our position of the particle at the beginning of our interval. So s at 0 equals 10. We need the position of our particle at the end of our interval, which would be 6, I believe. And then we need our position of the particle where our velocity is equal to 0. So 3 over 2. and this would be 49 over 4, which would be 12.25. So for a motion diagram, it only really has one axis, okay? And this is our position. And what we're going to put on is, what do I have to go up to? 14. 8, 10. Make it a little bit longer here. 12, 14. Okay, so then what we're going to do is I'm going to put on my particle. I'll just use a different color. I'll use red here. So at t equals 0, my particle starts at 10. Now I know that in the first half of my interval, my particle is moving to the right until its velocity reaches 0 and it changes direction. So I know it moves right until about 12.25, so about right here. So this would be t equals 1.5. Okay, and I'm going to connect this way. And then I know my particle moves back in the other direction all the way until the end of my interval, which is at t equals 6. Here. Okay, and this represents my motion diagram, where my axis down below represents the position of my particle. My dots represent the endpoints of my interval and where the particle changes direction, or the velocity is 0. That's a more accurate way to say that. And then the path of the particle, or the direction of travel, is represented by this line in between the dots.